Yeah, that's it. No, I've already figured it out. All right, so 108 is where it's going. All right, 108 when we're done. So we're talking about translations. Yesterday we talked about reflections. Translations are not new to you either. We're going to look at them a couple of the ways that you've already looked at them, but then also in a completely different manner. Using something that is brand new to you. It's not difficult, but just might look weird and just not fully comprehended at first. So I want you to look over here. I have this little grid. Here's what I didn't realize until last period when somebody said something. Your little grid didn't show up on the copy. Okay, because again, I don't know what's going on with my printer. It's only like really making things dark when it wants to. So, but there, what you have is on a grid, even if you can't tell that it's on a grid. So this red arrow here, geometrically, what does that represent to you? Array, right? Okay, so is that that's what you think of when you see that array? Okay, what does the arrow mean? Keeps going forever. Okay, so that's, if this was array, which it totally looks like one, and I would expect that that's what you would think, because that's the only thing that would make sense to you at this point. However, when we're on the coordinate plane and when we're using them mathematically like this, I mean, we use arrays mathematically like for angles and stuff, but we're using this thing itself. It is not a ray, and the arrow does not mean that it goes on forever. Okay, so what this thing is, we'll talk about what it is in just a second, but this point E, this is where we start, so this is called the initial point. The arrow is actually where we end, so point F is called the terminal point. I have no idea where on the coordinate plane that is, and it doesn't matter because the location is completely irrelevant. What matters and what this gives me is distance and direction, okay? So it's going to tell me where I'm going to move and how. So if I look at point E, and again, I know you don't even have a grid, but if I want to get from point E to F, I would have to go to the right 1, 2, 3, 4, and I'd have to go down 1, 2, 3. That make sense? And so if I, but I don't know where I started, it doesn't matter. If I said, okay, everybody stand up and we're going to stand inside of a square. We're not going to do this because I don't know that we make it, but if we all stood inside of a square and then I said, okay, we're all going to move to the right 4 and then back 3 squares. Then when we stopped, we'd all be in a different place, but we'd all still be the same distance away and we'd be in the exact same shape we were when we started. Does that make sense? Because we all moved the same distance in the same direction. So this thing, if I want to talk about how that's happening and I'm on the coordinate plane, then my x value is changing by 4 and my y value is changing by 3. Specifically, I'm adding 4 to the x value and subtracting 3 from the y value because it's negative, right? So I can write it as an ordered pair 4, -3. However, I'm not putting parentheses around it because if I put parentheses around it, that means that's a point I'm going to go and plot. And that's not what's really happening, right? It's possible that F could be at that point, but I have no clue and it doesn't matter and it doesn't have to be there. What it's giving me is my distance and direction, just telling me. That's like giving you directions to wherever you are. Okay, you're going to go, 3 miles north and 4 miles south or whatever. Then we do this so that it doesn't look like an ordered pair and it has these pointy brackets on it. The first number still is the x value and the second one is the y value, but it's not for the ordered pair that you're plotting a point for. Does that make sense? That is your change. It's like you're changing your x and you're changing your y. So this is how it looks like this. What this is called and what this notation is, this is called a vector. Okay? So a vector is a quantity. It might sound weird to talk about it that way, but a quantity that has both magnitude and direction. So distance and direction is what a vector gives you, not location. Ordered pairs give you locations, but vectors do not, okay? Now, vectors are very important because you don't talk about them in Algebra 2 at all. At the very beginning of physics, you're expected to understand vectors. In geometry, we're not expected to do much more than what we do today, which is not enough to get you started in physics, okay? So my plan this year was, because I didn't even realize that until a couple of years ago. I mean, I knew you did vectors in physics, but you also do them in pre-cal, but they are not done at the same time. You don't talk about vectors in pre-cal until January, and we do a lot with them, but not until January. But in August, you got to be able to be using them in physics. So I was going to go a little deeper into vectors so you had a better concrete understanding of them before you had to start using them in physics. But because this school year has been so weird, I don't know if I'm going to have time for that. I think I'll try to at least get something together where if you want to look at it and make sense of it, then you can. But if not, I mean, that's on you. But I do feel like, you know, there's just things don't always line up like we would like for them to. So vectors. Now, have you seen Despicable Me? Yes. What's the bad guy's name? Vector, right? And doesn't he say something about magnitude and direction in there? I don't remember his quote or whatever he says. Yeah, I know, right? And what does his shirt have on it? A V, okay? And there's arrows probably all over the place. They're really vectors. They're not arrows. And so, see, the more math you know, the funnier the movies get, right? Yeah, I know you have to go watch the movie again.
I was going to say it, but I was like, she's probably going to yell at me.
No, but that's a good question. That's not stupid. All right. So we're going to use these vectors today for translation. Now, vectors are used for lots of different things that are a lot deeper and different than this, but today we're using them for translations. And so our first definition here is of a translation. So a translation, which again, not new to you, is a transformation where all the points of a figure are moved the same distance in the same direction. That's what a translation is. And that's what a vector gives you, is distance and direction. So it's like a translation vector is all that it is. So a translation, since we would move the same distance in the same direction, that falls into a specific category of transformations. What were those called? Remember, it starts with an I. Isometry. I something. Isometry. So a translation is an isometry, so the image of a translated figure is congruent to the pre-image, right? Because we're just moving it. We're not changing the size or the shape at all. So next is a different definition of a translation, more vector-like definition. So a translation is a transformation along a vector such that the segment joining the point in its image has the same length as the vector and is parallel to the vector. Okay, so let's think about this. I could set this vector down anywhere as long as I didn't change the angle or the length, and it would mean the same thing. So if I start at point A right here, and I'm going to translate it along this vector, that doesn't mean I have to move it over here. What that means is when I finish, and this line segment here that connects the two has to be parallel to my vector, that means I went in the right direction, and it has to be the same length, and that means I went the same distance. That's what your distance and your direction is. So you'll look at a length and an angle measure when you look at it, you know, more mathematically than we're doing right now. But right now we're just going to look at them as coordinates, and we'll be good. Okay? Okay so far? Okay. So they're different, and they might look a little weird at first, but it's not going to be difficult what we're doing at all. So example 1 says to graph the triangle, translate each x-coordinate 4 units right. Now, this wording and what it's telling you to do is what you did before 8th grade math, when you first did translations, whenever it was. So we're going to start this way. First, the triangle's already drawn for you, so we just need to label it. So A, B, C. Then I'm going to take this, and I'm going to translate it. It says 4 units right. So I'm going to take point C. I'm going to count to the right 4 units. There's my C prime. Do the same thing for B. And do the same thing for A. And then I'm going to connect the dots. Yes. Yeah, A prime, B prime, and C prime. Now, what you also should have already really fully comprehended here is that since all I'm doing is moving 4 units to the right, my y values did not change at all, right? So for my original figure, my original points here, the y values all stay the same. And then what I did, since it's 4 units right, that's a positive 4, and I literally just add 4 to each x-coordinate. That gives me 6, 2, 9, 2, and 9, 5, and those are the points that we plotted over there, right? And it's a pretty basic thing. The other thing that you have done with this so far is the mapping notation. Now, I realize that nobody probably ever said to you what this means, and that's okay. This means it maps to, but you've seen the notation, even if you, and you knew what it meant, even if you didn't know how to say it. So every point xy, because we only plotted 3 points and connected the dots, but there's an infinite amount of points there, right? And so they all moved the same distance, the same direction. So every single x value has 4 added to it. So xy maps to x plus 4, comma, y value didn't change, and so it's just y. So all that so far should look familiar. Would you agree? Okay, so now what's different here is the vector notation. So I translated this along a vector. Well, my vector can be, I can start anywhere, right? So I'm going to start, I don't know, right here is fine. We'll start right here. And then I'm going to go to the right 4 units. And since I started here and ended here, here's my arrow, there's my translation vector right there. Right? And so my translation vector, to write it, it is, I use the little pointy brackets. I went to the right 4, so my x value is 4. I didn't go up or down any, so that's 0. So I translated it along the vector 4, 0. Does that make sense to you? And do you see how these two connect? I mean, if you can do this, you can figure that out. It's not that big of a deal. You just got to make sure that you're notating it correctly. Now, we could connect all of the vertices. I'm just going to connect C to C prime because the rest won't really come out that well here. But C to C prime, and that's just a line segment. I want it to be my vector, so I got to put the arrow in the right place. So I started at C and I went to C prime. That's what my vector looked like. If I put the arrow over here, that would mean I went to the left 4 instead of to the right 4. And then what's happening here is that these vectors are congruent and they're parallel. And if I connected A to A prime and B to B prime, the same thing would happen. They would just overlap down there and look weird, so we're not going to worry about that. But so in general then, because this right here is specifically for this graph, my vector, all that changed was the x value, so that would be some value a, and then 0 for the y value. Your mapping in general looks like this, x plus a, comma y. Everybody okay with all that? Any questions at this point? Alrighty, let's look at the next one. So this time we are going to translate each point 4 units up. So the first thing I'm going to do is label, this is the exact same triangle, I just use the same ones because it just makes it easier to get things graphed. So then each point, excuse me, we go C, I'm going to count up 4 units, that's where C prime is. Do the same thing for B, and then do the same thing for A. Use your straight edge to get it drawn in. So I was supposed to just translate up 4 units. So right there, there's my 4 units. And I can also connect A to A prime. And again, I could do that with all 3 of them, but things that overlap, it would just look weird, I think, for you on there. And I know here then that these are congruent and they're parallel. So my ordered pairs, A prime, my x values all stayed the same, right? And my y's, I added 4, so this becomes 6, 6, and 9, right? So what do you think my vector looks like here? What would the vector be? 0, 4, good. And x, y maps to x, comma, y plus 4. So that's specifically for this graph. In general, if all you have is a vertical translation, then your vector is 0b, and your mapping xy maps to x, comma, y plus b. These two things essentially say the exact same thing, they just say it in a different way. Yes. We good? All right, so example 3. This time we are going to translate each point 5 units right and 4 units. So we're getting crazy here. We're going to go to the right and up at the same time. I know, it's getting a little out of control here. All right, so I take C. I'm going to go to the right 5 and up 4. Now, instead of counting from each point, which I totally can do, but once I get one of them, these two triangles are going to be congruent, right? And if B is 3 units down from C, then B prime is 3 units down from C prime. A is 3 units over, so I'm going to go 3 units over, and then I'm not going back and counting from scratch every time. There's lots of different ways to approach it and be correct here. Connect my dots. And then this time, we're going to get crazy again, and we're going to connect all of the vertices. So I'm going to connect C to C prime, A to A prime, B to B prime. If you want, I would suggest maybe you use a different color or you make them dotted lines maybe, just so that it doesn't get too, otherwise you just have pencil lines all over the place. And when you do that, it's kind of an exaggerated example, but do you see how you could use that to draw three-dimensional figures, to draw your prisms? Yeah. It's like a triangular prism. And so that's why sometimes when you draw the prisms by hand and they look like all crooked and wonky, that's because everything isn't the same distance in the same direction away. You know, one of the little segments is a little too short or something, and so it just kind of makes everything look weird. But if they all go in the same distance in the same direction, then you're good. Okay. You don't have, when you do the rest of these, you don't have to draw, you don't have to connect these points, because that's just going to make it worse depending on what you have and what you're doing with it. But at the very least, I want some random one on your paper. So if I start here, what was it? I'm going to the right 5 and up 4. So that should be, you should have a vector somewhere, and yours can be at a different place than somebody. I mean, on here, go ahead and do the other ones, but like on your homework, you don't have to draw in every single one and an extra one. That's just too much and not necessary, really. But I do want you to have a random one somewhere, because I want you to understand that the location of the vector does not matter. It's just giving you distance and direction. Okay. So my vector notation then, what is the vector? 5, 4. Right? And that, just like the mapping notation, tells you exactly what to do with your pre-image points to get your image points. You add 5 to the x value, 4 to the y value. So this becomes 7, 6, 10, 6, and 10, 9. Yes, just like when you plot points, it's always x, y. And if it's negative, then you would go left or down, depending on which one it is. Okay, we all good? All right, so then our mapping notation, which again, not brand new, x, y, here specifically maps to x plus 5, y plus 4. Then generically, any translation vector would be AB, and then the mapping x, y would map to x plus a, y plus b, understanding that a and b could be negative, so that could change to minus. This right here is really the rules. Because I wanted you to see the horizontal and vertical before we went crazy and went diagonally, we wrote them the other way, because if b is 0, or a, the one right above here, a was 0. So I don't put x plus 0 right here. I just put x, right? But I can have a, b, and a or b could be 0 as well. And there's really just one rule. Okay, we all good on that? Any questions at all? All right, awesome. All right, so then this one here, we have to start off by actually plotting these points ourselves. It says translate the figure with the given vertices along the given vector, state the coordinates of the image and the mapping. So I first have to plot these, because it's not plotted for me, 2, -4, and that's point A. So plot and label at the same time. B is 1, -2. C is 3, 0. And then I connect the dots. Okay. So what I'm going to need in the end, I'm going to need A prime, B prime, and C prime. And then I'm also going to need the mapping, which means that's X, Y maps to something, whatever it may be for this one. So my C, I'm going to take C, I'm going to go, that -2 means I do what? Because this is my vector. I'm going to go to the left 2 and then up 4. So this is C prime. I do the same thing for B. To the left 2, up 4, and then the same thing for A. To the left 2 and up 4. And when you're plotting the points, just counting from the graph, most of the time is probably the easiest, just depending on what's happening. But if you don't have to have a graph or whatever, when you go to figure out everything else, this vector you can very easily change to mapping notation, right? Because this is just going to be X something, comma, Y something. And then this is a -2, so it's X -2 and Y +4. And both of these, but in different ways, tell me exactly what to do with these ordered pairs to get my primes. I have 2, -4, so I take the X, I subtract 2, 2 minus 2 is 0. -4 plus 4 is 0. B, that's 1 minus 2, so it's a -1. -2 plus 4 is 2. 3 minus 2 is 1. 0 plus 4 is 4. So I got my graph by counting things, and then I got my points by looking at the vector or the mapping. It doesn't matter which one. But then I can use that, since I did both ways, is to double check myself. My A prime should be at 0, 0, and it is. B prime should be at -1, 2. C prime should be at 1, 4. And I could have gotten these first and just plotted those points. That works too. Okay. We did, didn't we? Well, that's because in general it's A and B. Oh. Here, we did right here, see X plus 5 and Y plus 4. Oh. I did specifics there, but because these numbers could change. And so that's why we used A and B. That's a good question. Okay. But what is missing from all of this? The vector, okay? So I need a vector somewhere, okay? I mean, it doesn't matter where. You don't have to connect these. I'll start here. I'll start here, and I'm going to go to the left 2 and then up 4. There's my vector. And then, so you should be able to see from that every point, if I connected those vertices, they would all be parallel to that vector. Okay? Any questions at all? Alrighty.
Wait, this is going to have to be a point as a dot?
Like a dot? Is that what you mean? No. There does not have to be a dot here to start because it's not array. It's just like that without a little dot. Okay, no dot. Okay, anything else? Yeah, you can do the vector wherever. As long as it's parallel and congruent, yes, everybody in here can do it in a different place, and it's absolutely fine. All right, so on the next one, I'm going to let you do this one while I pass out the homework and take attendance and stuff. But make sure that you have all of these things. You're going to have R prime, S prime, T prime, U prime, and then your mapping. Make sure they're both drawn and labeled. And I'll give you a minute to do that. So you want to know what the most common mistake on this one is, which I've seen multiple times today? People graphing a triangle. Okay. There are 4 points. Make sure you plot 4 points. And if you're erasing right now, you're not alone. So.
Yeah, I just graphed that.
Yep. Okay.
I got my vector right here.
S-T. And your vector, you don't even have to wait until the end to do your vector. I mean, I could have drawn my vector at any time, so you can do it before you graph any of the stuff if you wanted. I mean, that may not be the best idea because you don't know if it's going to be in your way or not, but vector is -4, -3, so we'll start here. -4. That'll work. I know. I've done this. It's not my first rodeo. All right, so then I'm going to go. All right, so that is what I got. Ooh. All right, so do you have any questions? Is this pretty simple still? I mean, it doesn't really complicate translations that much. It's just a different way to notate this. And then vectors, again, have way more stuff going on with them down the road. If you will grab the assignment I put on your table, I want to talk you through it real quick. 1 through 4, just like yesterday, the key word there is appears. So tell whether each transformation appears to be a translation. Obviously, they would have to be congruent, and so you're allowed to kind of assume on that. 7 through 10, you're translating it with the along the given vector, but down at the bottom it says, for 7 through 10, write the ordered pairs for the vertices of the image in the mapping next to the graph. Make sure you graph and label the pre-image and the image. So basically, everything we just did on this example has to be done there. You write this stuff out, write your mapping, graph them and label them both, and do your little vector. Yes, ma'am. Ah, did I miss the whole table or just you? The back, just make sure you're reading the directions, because I think you can handle it if you can read directions, and you're good. Any questions? All righty.